if that's okay with you. So the rest was off the of the record. So it's my pleasure to introduce Denis Demchenko. Denis did his master's degree in '96 at Odessa State University. He told me his family is all right.
Yes.
He did his PhD in 2002 at South Dakota School of Mines and Technology with Andrei Petukhov, who some of you may remember was in our group here for a while and was an adjunct professor in our department for a while. And then he did 2 postdoc stints in Georgetown University and then at Lawrence Berkeley National Lab. In 2008, he joined Virginia Commonwealth University in Richmond, that is, right?
Yeah, that's right.
And then was promoted and got tenure there in 2014. And he's been working on various aspects of computational solid-state physics materials, nanoscale systems, thermal conductivity. While he was at Lawrence Berkeley, he worked on copper sulfide and things. And we had some overlaps of interest over the years. And in the last few years, he has worked extensively on doping and defects and trying to understand experiments on those topics in wide bandgap semiconductors such as gallium nitride. And it's one of those stories I think he's going to tell us about today. Okay.
Thank you very much, Walter. Yes, I'm going to share my screen with you and go from there. Okay.
Probably you need to make a Denis co-host as
I think now it works.
It
works.
Yeah, you can share, yeah.
All right. So what I will talk about today, for the most part, is the difference between shallow and deep states of acceptors of gallium nitride, and why photoluminescence experiments do not show small polaron for defects in gallium nitride at least, but I believe this is a more general phenomenon. There's a range of defects where this is true, and I will try to explain what we think currently about this and how all this works. I am from VCU, Virginia Commonwealth University, and this work was supported by NSF. We are grateful for that. I see that most people here are actually faculty, but I have prepared this talk where I'm going to be explaining some things that are maybe too elementary for you. So I'm hoping maybe there's a couple of students in the audience that will find it at least useful. Okay, to start with, gallium nitride is incredibly important for light emitting applications. So I got these pictures yesterday from Walmart website, where they're selling these LEDs that are based on gallium nitride alloys, and their cost approaches incandescent light bulbs. You can buy 4 of them for about $5. It's a great price. They are very efficient, as you can see, only 9 watts, which produces incandescent 60 watts equivalent of light. They're non-toxic. I still have fluorescent lights in my office, which have mercury in them. And the goal is, of course, to replace those with LEDs that are much better for environment and much more economical. However, if you look at these 2 reviews on the same website, one after another, one guy loves it, 5 stars, bright lights consume little energy. The other guy hates it. He says that great bulbs if you enjoy changing them within a couple of months of buying. So it's not really working great. But here, since I'm talking to professors and not students, I have to come clean, I guess. This is not a material science problem, really. My electrical engineering friends are telling me that there is a little transformer in there in each of these LEDs that down converts voltage from 120 volts to whatever this little LED requires. And usually that's what goes. And this is why they burn out. It's not really gallium nitride problem per se, but there's room for improvement. Next, what I'm going to show you is actually a material problem, which we'll need to work on. Overall, gallium nitride based LEDs are a huge market. So almost $1 billion in 2016, and it's growing. I don't really know the recent number, but it should be in the billions now. And it's mostly because of this, because now these bulbs are everywhere. In fact, if you go to any store, most of the lights you would buy there are LED lights. So that is kind of a more maturing technology. But the emerging technology, which is even more exciting, is ultraviolet LEDs. Now, ultraviolet LEDs would be also based on gallium nitride alloys, GaN in particular, where the band gap is bigger, so you can produce ultraviolet light. For these devices, they do exist. However, their efficiency is really low. We will look at this picture where we have efficiency versus wavelength. They're mostly hanging around here, like below 10%. And in fact, for most ultraviolet LEDs, it's around a few percent. Target efficiency should be around 30 or 40, but they're nowhere near that just yet. And there is a material science problem there. The reason why they're not that efficient is because there is no good P-type material that is gallium nitride based. And this is, if this was true, if people could work out these problems, there's so many applications for these ultraviolet LEDs. Gas sensing, plant growth lighting, curing by UV, air and water purification, large-scale disinfection. We all, during COVID, we were in my gym, we had to spray everything with alcohol. And they were showing pictures in New York Metro, how people were spraying metro cars with alcohol. You wouldn't have to do that if you had cheap and powerful ultraviolet light. You could disinfect surfaces much quicker and without using chemicals. Yeah. Well, that's not existing yet because these LEDs are very inefficient. Bad P-type material is the root cause of the problem. Bad P-type material means low efficiency. And here's why. I'm going to need to move this out of the way, maybe over here. Excuse me for a second. I'm trying to play with, Zoom wouldn't let me. Okay, let's do it like this. N-type gallium nitride is really easy to make. Pretty much anytime you grow gallium nitride, it usually comes out N-type because there are natural N-type dopants. Oxygen is oftentimes present. Oxygen is a shallow donor in gallium nitride. You can also intentionally dope it, make it N-types doping with silicon or germanium. Also, there are native defects in gallium nitride that make it N-type. Nitrogen vacancy, which is, well, for some regimes of growth, is ubiquitous. And it's a shallow donor, so it creates N-type GaN, gallium nitride. P-type gallium nitride is a huge problem. Good P-type gallium nitride still does not exist. In fact, the only P-type dopant that works in gallium nitride right now is magnesium. Magnesium, for which Suji Nakamura got a Nobel Prize in 2014. They figured out the way to activate this P-type conductivity in gallium nitride. The way they did this, there are several different approaches, but one clever trick is you grow a material, dope it with magnesium, co-doping with hydrogen. And the problem you're trying to solve is that if magnesium goes into gallium site, so for example, this defect here, the way it's labeled, magnesium with gallium subscript, that means magnesium on gallium site. If it's like that, it's an acceptor. But if magnesium goes into interstitial site instead, where it also has relatively low formation energy, it's a shallow double donor. So magnesium acceptor kind of kills itself during growth, and usually samples come out to be high resistivity. But if you co-dope with hydrogen, hydrogen-magnesium complex is electrically neutral. And so it comfortably goes into gallium site, sits there, sample comes out high resistivity, and then you anneal it, get the hydrogen out, and activate P-type conductivity by basically isolating magnesium acceptor. And that's what made the breakthrough for P-type gallium nitride. Indeed, that's how we got blue LEDs and stuff like this, Blu-ray players and all that. But it's still not good. The acceptor level of magnesium acceptor in gallium nitride is 0.22 electron volts. That's deep. It's not really great. So you need very high concentrations of magnesium acceptor in order to have any sort of decent P-type conductivity. And anytime you have very high levels of doping, you reduce crystallinity, the quality of the material suffers as well. And so it's a balance that people are trying to play with. It's highly desirable to have something shallower than magnesium. And currently, we are looking at beryllium. Beryllium is right next to, right under magnesium on the periodic table. So the very similar chemical properties. Really, the only difference is the size of the atom. Maybe it's an alternative, and that's what we're trying to explore here. However, recent first principle calculations that are usually done with hybrid functional theory that I will be talking about later, they predicted pretty much across the board acceptor level of beryllium acceptor much deeper than magnesium at about roughly 0.5 eV, from 0.45 to 0.65, above the valence band. This deep acceptor state originates from so-called small polaron. Small polaron is a hole that is self-trapped by a very large lattice relaxations. So what happens is if you put a hole on this acceptor, make it neutral, there is a lattice geometry of this defect where one of the bonds between beryllium and nitrogen gets stretched by a lot, by roughly 0.7 angstroms. And that stretching creates a local minimum where hole gets localized. And that leads to this very deep state of acceptor. This prediction also leads to predicted optical transitions through this defect. So you excite electron-hole pair across the band gap. The negatively charged acceptor captures the hole, and then electron recombines with it, emitting light. This photoluminescence was predicted to have maximum at about 1.5, 1.8 electron volts, and zero phonon line, that's basically this transition. I will explain what zero phonon line is in a few minutes. It's about from 2.9 to 3 electron volts. However, there is a controversy. On one hand, indeed, nobody succeeded making a p-type by doping with beryllium. So that suggests, yeah, maybe that's a deep acceptor. But on the other hand, this photoluminescence that theory predicts is not observed in experiment. So it's strange. Where is it? In fact, due to these predictions were done over the years many times, mostly from theory. The research in the direction of beryllium has been largely abandoned. And I think it deserves a second look. Now, how this defect photoluminescence works. There's a couple of different ways to look at it. If we excite electron and hole across the band gap with a laser, usually this is done with a laser that shines, with energy larger than the band gap, then electrons and holes thermalize by releasing energy to the lattice. And then there are two possibilities. The defect can act as a either radiative or non-radiative recombination center. So this recombination that I'm drawing here. So this is a non-radiative recombination. The hole can be captured non-radiatively, and then electron can be captured non-radiatively, releasing energy as phonons into the lattice. Or electron and hole can recombine radiatively across the gap, basically giving radiation with energy of the band gap slightly lower, because usually at low temperatures they form excitons, but let's put that aside. Or this defect can also act as a radiative center. So if this is my defect level, hole again is captured non-radiatively usually, and then electron recombines with it radiatively, producing this PL. The way this works in real space, so if this is my hole, that's local. This, by the way, actually, that's not an acceptor. This is the picture of nitrogen vacancy. But we can pretend that this is some sort of acceptor. We have a hole that's localized in some place. Then it sits there for a while. Then electron comes by and they recombine, emitting light. Now, there is a better way to look at this, because this picture right here, it's static. It doesn't really show you the full picture of photoluminescence. The way to look at it is from the point of view of configuration coordinate diagram. And this is what's plotted here. Now, this is going to be a busy and cluttered slide, unfortunately, but hopefully I can draw things that I want to show. So if this is my defect, suppose this is an acceptor, and if my, say this is conduction band, this is valence band, and suppose I am considering some high resistivity sample. So my Fermi level is somewhere in the middle of the gap. My acceptor level is over here. So that's 0 minus transition level. In a picture like this, the acceptor level must be full with an electron. So it has charge state of -1. So my ground state of acceptor, all these atoms around defect, they vibrate in a bunch of vibrational modes, but we can pick up some sort of effective mode of vibration and plot this vibrational problem. So this is going to be -1 state of acceptor that sits there in the dark with a bunch of vibrational levels that are separated from each other with some effective vibrational frequency. If you shine a laser at a sample, now you create electron-hole pair. The energy of the system is raised by the value of the band gap. So I now need to draw this adiabatic potential, this vibrational potential up here, raised it by energy of the band gap of gallium nitride. It's exactly the same parabola, but now this is -1 plus gap. And the vibrational system here has some Gaussian vibronic wave function where it sits and vibrates up until it's still negatively charged. So it's attracting photogenerated hole up until it captures this hole and would become neutral. This parabola right here, this is the neutral state of acceptor. So the system has to jump from this negative parabola down to this neutral parabola. This happens by multi-phonon emission. So if the way I drew this, there's basically no barrier to transfer from -1 plus EG parabola to 0 parabola. So this happens pretty efficiently and pretty quickly. And the defect emits a bunch of phonons and gets into vibronic ground state of neutral state now. Now there is two possibilities. You can either get straight down to the ground state, negative ground state, by emitting a photon, and that would give me PL maximum. Or because there is a spread in vibronic wave function right here, you can, the peak is right here, so this is where most of the photons will be emitted, but there is some probability over here, so some will be emitted right here, some will be emitted right here, and so forth and so on. I have all of these possibilities. The largest energy transition is called zero phonon line, ZPL. That's the transition from vibronic ground state of neutral state to vibronic ground state of the -1 state. So that's, n equals 0 to n equals 0. And then the next energy that's slightly lower in energy by 1 vibrational level is called first phonon replica. And then second phonon replica, third phonon replica, and so forth and so on. This sum of all these transitions, it forms the photoluminescence band. There's another possibility, however. The system can also transfer from the neutral to the negative ground state by doing it non-radiatively through this intersection of these two parabolas. In this case, though, the way it's drawn, you can see that there is a potential barrier for that transition. The system would have to overcome it somehow, one way or another, maybe with temperature or maybe tunneling. Usually it's a combination of both. And this can be taken into account. I will be talking about this a little bit later, how to calculate that. But basically, when this barrier is pretty big, say bigger than 0.7 eV or so, the system is stuck here and the transition is going to be radiative. If this transition barrier is lower than, say, 0.5 eV or 0.4 eV, most of the transitions are going to go a non-radiative route, and the defect will act as a non-radiative center. So there's this competition between radiative and non-radiative paths. You can calculate radiative transition rate and non-radiative transition rate and see which one wins, and that's going to be the radiative or non-radiative center. One last thing I want to mention is it's interesting that photoluminescence is actually direct observation of a quantum mechanical phenomenon. Now, this is not as messy. This is my ground state of the neutral vibronic wave function. This is my 0. This is my -1 charge state of defect. Basically, photoluminescence band is a projection of this vibronic wave function, Gaussian, down to the ground state parabola. So you'll get some shape of PL, which then, as you measure it, looks like this. This happens to be zinc acceptor, but it's a very nice illustration. This shape is the Gaussian of vibronic wave function projected on the ground state parabola. And then these little peaks right here on the high energy side, that's ZPL. The next little peak separated by phonon energy, that's first phonon replica, second phonon replica, third, and so forth. So this is sort of moderate case. In some cases, PL bands are so wide, like for this one on the left, where you just have a smooth spectrum and you don't really see zero phonon line, it all gets washed out. In some, usually this, by the way, happens when the separation between these two parabolas, by the way, I did not draw your attention to what's along the x-axis. Along y-axis, it's energy, but along x, it's what's called configuration coordinate. It's basically a mapping of all of these coordinates of all of these atoms onto one-dimensional configuration coordinate. And there is a neat way to map that on one-dimensional problem, which I'll briefly mention in a few minutes. So what I'm saying is, if these two defect charge states, 0 and -1, are separated by a large configuration coordinate Q, you usually get these very wide bands, wide PL bands. If they are not separated by a lot, they're basically right on top of one another. That's usually the case for shallow defects. You get this very, very sharp PL band where ZPL is a very high, very well resolved peak. First phonon replica is well resolved, second phonon replica, and so forth. And if it weren't for this band that covers it up, they would keep going farther and farther. So how far these parabolas are separated from each other, in other words, how much crystal lattice is different for -1 and 0 charge state, affects the width of the photoluminescence. Now that we have all this introduction, let's look at what happens if we dope gallium nitride with beryllium. What kind of PL spectra we get? We get the following picture. So here, at the highest energy, the band gap of gallium nitride is 3.5 electron volts. So this is where band gap is. Slightly below is what's called a donor bound exciton. This is believed to be the case. I mean, if you resolve this further, there is also free exciton there and a bunch of other excitonic structure, which we don't really care about because that's not really defect related. Now lower, right below it, is 0 phonon line of UVL, ultraviolet band of beryllium. You only observe this band in beryllium doped sample. It comes from beryllium. This is its first phonon replica, second phonon replica, and third phonon replica. They're really well resolved. And this is a signature of a shallow acceptor. This means that these two parabolas of ground state and excited states are right on top of each other. That means lattice does not really distort when you put electron on it, because wave function is very spread out, and that's a shallow defect. So that's already sort of strange. Theory predicts beryllium to be deep, and yet we clearly see a very well pronounced shallow defect state of beryllium acceptor. Another defect luminescence band is yellow due to beryllium as well. Also only observed in beryllium. This definitely comes from some deep defect. It's a very wide band. That means there's significant lattice distortions that happen there, and well, needs to be identified. Where does this come from? This band, however, does not agree with PL band predicted from theory of the polaronic band. I'll be talking about that too. Finally, red band, also wide band due to beryllium, only observed in beryllium beryllium doped samples. So also needs to be found. This guy, GL2, that's green luminescence, and we have identified it some years ago. It comes from nitrogen vacancy. So that's not beryllium related. But these three are. One thing to be to keep in mind is that these 3 bands come from 3 different defects. Why? Because in different samples, and my experimental collaborators have measured hundreds of them by now, the intensities, relative intensities of these PL bands are all over the map. They differ by 6 orders of magnitudes in different samples. So I will explain a little bit later why from Shockley-Reed Hall recombination picture that means that these are different defects. These cannot be states, different lattice states or different charge states of the same defect. Okay, let's keep that in mind. If I now, I want to try and convince you further that that UVL, ultraviolet band, is indeed from shallow beryllium acceptor. How do I know this? All right, so now if I zoom in into this, I see the following fine structure of this ultraviolet band. Now, this is donor-bound exciton. This is free exciton peak. Now there's this so-called 2-electron satellite. We don't care about any of this. These are excitonic structure. We want to concentrate on this. This is coming from beryllium. At low temperature, so for example, if my measurement is made at helium temperatures, 18 Kelvin, all the electrons, and if this is n-type sample, this is done in n-type sample, so this is my band structure. This is valence band, conduction band. Now I have a bunch of donor levels. Fermi level is somewhere over here. And so that means my donor levels at low temperature are all filled with electrons. Here's my acceptor level as well. If now I apply electron hole, I shine the light at this, electron hole pair is created, hole is captured by the acceptor. And then what usually happens, it's not the free electron that recombines with the hole in the acceptor. It's the electron that sits on one of the donors recombines with this hole. And so this is called donor acceptor pair recombination, DAP. This is indeed what you observe with this blue line here at low temperatures. Then you start increasing temperature at 55 Kelvin, you get this red line. You see, it's shifted to higher energies. That's because now electrons are thermally ejected into the conduction band. And now it's the conduction band electron that recombines with the hole localized on the acceptor, which is why it's called this EA recombination mechanism, where the peaks are slightly shifted by the depth of the donor level to slightly higher energies. Now, this behavior is a fingerprint of an acceptor behavior in gallium nitride in general in semiconductors. The exact same thing happens for magnesium, for zinc, for carbon, for all of the acceptors in gallium nitride. So this PL band comes from an acceptor, not from a donor, not from a complex, not something. It's a beryllium-related acceptor. And if you look at the zero phonon line, which is this transition, and how far away it is from the conduction band, you get 113 millielectron volts as the depth of this acceptor level. This is astonishing result because it's the shallowest acceptor known to date in gallium nitride. It's 2 times better than magnesium. And so first of all, great. So why don't the samples, if you dope them with beryllium, why don't they come out p-type then? What's the problem? Number 1 question. Number 2 question, where is deep state predicted by theory? What's up with that? Now, let's look at how we can explain this theoretically. I'm not going to talk a lot about this particular thing because I mean, all faculty know this, students probably do too, but how do we calculate defects? Well, all defects in the solid usually sit in a dilute limit. Your typical concentrations of beryllium in these doped samples, well, 10 to the 617, 10 to the 18 is kind of as high as you can go, 10 to the 16, something like this. So that means that these berylliums are really far away from each other. They don't see each other, they do not interact. So you have to mimic dilute limit somehow. So that means you need a relatively large supercell. You put a beryllium atom in there, and you try and calculate something like a Schrodinger's equation for all the electrons in such supercell. The trouble, of course, is that this is a very complicated many-body problem. In fact, it's not even, I mean, the wave function for such problem would be so big, you wouldn't even be able to store it. It's enormous. So you can't do it. We have to resort to approximations, and the workhorse of solid state theory these days is density functional theory, where we basically reduce it to a single particle problem for some approximate form of potential that we solve this or similar equation for. Now, density functional itself, now I'm running into problems with my Zoom covering up. Hold on a second. Okay, there we go. Density functional itself, in its simplest approximations that we've been using for decades now, and that's local density approximation or general gradient approximation. It has a problem. It has a problem in that it's very famous thing. It underestimates the band gap. So in this Jacob's ladder of methods that could give us better and better accuracy, and this is John Purdue's illustration, where below is the very inaccurate Hartree world of unrealistically weak or missing bonding. Then you start climbing step by step this Jacob's ladder to heaven of chemical accuracy, where we're not there yet, as far as defect are concerned, that's for sure. But with local density or with generalized gradient approximation, where you assume that an electron is interacting with average density of the rest of the electrons, and in the first step, it's that all that matters. In the second step, you also take into account the gradients of that density. The trouble is the band gap is very underestimated. So here's the illustration. Here's theory versus experiment as far as band gaps are concerned. And these blue dots are GGA calculated. PBE is one of the versions of this general gradient approximations. You see how all of these blue dots are significantly lower than the perfect agreement of the red line, especially for white band. Zinc oxide, for example, is one of the worst examples. Gallium nitride is not that bad, but still it's a problem, because imagine what happens if I have my band gap that's too small and I have my acceptor level over here. If this is correct band gap, then everything's fine. But now if my band gap is too small and my levels are somewhere over here, so this is valence band, this is conduction band. Now my acceptor level can start hybridizing with valence band states. It may get some artificial delocalization. You will get wrong wave functions of defect state. You'll get wrong wave function, wrong charge densities, wrong forces, wrong lattice relaxations, wrong everything. So in some lucky cases, it may work if your defect level still ends up somewhere in the gap, but it's a dangerous thing to do. So the gap is important to make it as close to experiment as possible. And that's why in defect physics, pretty much everybody, almost everybody, I would say maybe 95% of people are doing hybrid functionals. What hybrid functionals do is they improve treatment of electronic interactions in solids by explicitly calculating exchange interactions and then screening them out at long distances. That's really what should be done to mimic, to mimic exchange interaction and correlations. Exact exchange, and then screen it out at long distances. So I'm not saying hybrids do it right, but it's better than ignore it altogether. And here's the result. Black triangles is hybrid functional calculations of band gaps of a bunch of different materials. As you see, they are much closer to the red line. Still not quite perfect, but much better. Now there is hope that you may get the defect level right. You can even tweak these hybrid functionals, a tweak amount of exact exchange in them. Exact exchange there is not at 100%. It's entering there with some fraction, usually a quarter, 25% of energy is calculated from exact exchange. But you can change that number. You can treat it as an adjustable parameter and make your gap agree with experiment perfectly. And that way you hope that, okay, this is my gap that is correctly calculated with respect to experiment. Here's my defect level and my results are going to be perfect. Now, is that the case? Well, yeah, so this is called hyper GGA. Is that the case? Turns out, no, that's not the case. If only it were that simple. Here's an example of, in my opinion, how to improve things. Because if you fit the band gap with your hybrid functional theory, what happens is you violate Kukman's theorem. In solid state, if there are any students in the audience, there is Kukman's theorem that tells you that an eigenvalue has to be equal to the total energy difference between total energies of empty eigenvalue and filled eigenvalue. That's the Kukman's theorem. The problem is if you fit the hybrid functional to reproduce correct experimental band gap, that theorem is violated. In other words, if this is my transition level between, n and n+1, so in case of acceptor, n would be 0 charge state, n+1 would be -1 charge state. This is the transition level. You put an electron on it, the eigenvalue goes down. You take an electron out of it, eigenvalue goes up. And so, as you can see, these eigenvalues are not equal to the transition level. Kukman's theorem is violated, which means, by the way, that in our electronic interactions, we are really doing something wrong. Because why that happens is because when you put an electron on an orbital, the orbital relaxes a little bit. So there is relaxation energy associated with it. But in our density functional approximations, there's also self-interaction. Wave function relaxation is negative. Self-interaction is positive. Those two things compete with each other. And so in this case, if the eigenvalue is too low with respect to transition level, that means I have too much wave function relaxation in my orbitals, and I suppose not enough self-interaction. If I made those two things equal to each other, self-interaction would be killed completely. And this is fitting Kukman's condition. And you put an electron on an orbital or hole on an orbital, it's equal to transition level, and eigenvalue does not move. In this case, effectively, you remove self-interactions from defect orbitals, and your defect level hopefully will then be better. It comes at a cost, however. Your band gap is a little wrong. In fact, for gallium nitride, experimental band gap is 3.5 electron volts. And if I fit Kukman's condition for it turns out the same parameterization of HEC fulfills Kukman's theorem for a bunch of different defects. It's not completely universal, but it holds for an array of them. My band gap is equal to like 3.25 electron volts or so. So I do underestimate the band gap by some amount. It's not too bad. It's not nearly as bad as local approximations. But that's the price I'm willing to pay for self-interaction free defect orbitals. That's at least the thinking. And I think it's a better thing to do when we calculate defects. Okay, now here's the illustration of how this is done accurately by calculating larger and larger supercells, where we calculate energies with respect to, this is 1/, size of the supercell, so infinite supercell is right here at 0. If I fit band gap, so this is correct experimental band gap, my eigenvalue doesn't really change much with supercell size, but uncorrected transition level, and this is corrected transition level. There are ways to do these electrostatic corrections in supercells because you're putting a charge on the supercell, and we usually do periodic boundary conditions. That means this charge is repeated in all directions to infinity, and that leads to errors. There are ways to correct them. So as you can see, these two are not really the same. There is difference between them. This is by how much you violate Kukman's theorem if you fit the band gap. They are not the same at the infinity either. But if I do sort of my own parameterization of HEC that does fulfill Kukman's theorem, my eigenvalues and my transition levels are exactly the same. Here at 300 atoms and at infinity as well. In fact, 300 atoms seems to be a very accurate sort of the size of the supercell that leads to very accurate results. And that's what we end up doing. I'm going to not talk a lot about ionization potential in this case, because I'm going to run out of time. But what I want to say is that ideally, I would want my conduction band to be such that my ionization potential is also correct. The problem with gallium nitride, however, is that ionization potential from experiment is really not known. There is huge scatter in experimental results from 6.2 to 7.2. There's 1 electron volt is the uncertainty of ionization potential for gallium nitride. So it's really hard to make a case that this particular HEC parameterization gives you correct position of the valence band. I cannot really claim that. All right, so that's the method. Hybrid functional is parameterized such that it fulfills Kukman's theorem. We calculate total energies for beryllium acceptor and for a bunch of other defects as well. We construct configuration coordinate diagrams by calculating total energy minimum in -1, total energy minimum in neutral charge state, and then in this same lattice geometry, I can calculate -1 as well. This gives me this point. I can fit a parabola in this point. I can also calculate neutral in -1 lattice geometry. That gives me this point. I can fit a parabola in this point. And so that's how you construct configuration potential diagram. And here you can see, is this barrier big or small for non-radiative transition? If it's big, it's going to be radiative. If it's small, it's going to be non-radiative. And also you can see whether the hole will be captured efficiently or there is a barrier for capture of the hole here. You can then calculate PL maximum. You can calculate energy of the CPL, phonon replicas, and a few other parameters as well. So Frank Condensed shift, this is relaxation energy upon luminescence, which has to do with bandwidth of the PL band and such things. And compared with experiment. I'm going to skip this. This is has to do with electrostatic corrections and how to do them right. This is the equation how the mapping is done from positions of all the atoms in the supercell to a single effective configuration coordinate. It's basically trying to fit it into a simple harmonic oscillator. Results. What happens with beryllium? People have noticed this before. This is not our invention, but people know this, that there is dual nature of acceptors in wide bandgap semiconductors. Beryllium is such example. I can start my lattice relaxation by HEC, by hybrid, from ideal gallium nitride lattice geometry. Just put beryllium in there and let go all the forces. If I do, my wave function becomes very, very delocalized, and the beryllium hardly relaxes. It creates some energy minimum where it shows a shallow acceptor state. It's still somewhat overestimated in our supercell calculation because we cannot really fit this shallow wave function in our supercell. It's too big, which is why this transition level that's calculated, it's too big compared to experiment. But we can clearly see that this is a shallow state. And in fact, recently people have suggested how to do this number correctly. You have to calculate big and bigger supercells and then do extrapolation to infinity to get the acceptor level right. I haven't done that, but it's not that hard. We could do this. And there is a second state of, and by the way, this is neutral state of this acceptor. And this is also neutral state of this acceptor. If I start relaxation of the lattice by stretching this beryllium nitrogen bond by a significant amount, say 0.7, 0.8 angstroms, it turns out that there is another energy minimum there in the same charge state. And wave function collapses onto this neighboring nitrogen atom, or as we say, it self-traps itself by a strong lattice relaxations, thereby creating a small polaron. So it's not a regular polaron where electron is moving through the lattice, polarizing the lattice. It's called a small polaron where the hole is sitting there and due to large lattice relaxation. This is what theory predicts to be the ground state of acceptor. And we agree with all the theorists that did this. We get similar result. It's just most theorists do not predict this guy because maybe people just didn't look. They found this to be ground state, which is correct. And this happens to be metastable state, maybe just missed it. But now there's two of them. So this one creates ultraviolet PL in experiment. This one does not. Why? Let's look carefully at configuration coordinate diagram as computed by HEC for this beryllium acceptor. All right. Again, suppose my sample is N-type or high resistivity, something like this, and Fermi level is somewhere in the middle of the gap. That means ground state of this beryllium acceptor is negative. So this is my ground state adiabatic potential. Now, electron-hole pair is created. If I shine a UV laser on it, energy is raised by the EG. So it's the same parabola up here that's dashed line, except higher by 3.5 electron volts by the band gap of gallium nitride. From here, photogenerated hole can be captured by two different states of acceptor I just showed you, by shallow state and deep state. Shallow state is big and delocalized. Deep state is very small and very localized with very large lattice relaxation, very large lattice distortions, which is why it's really far away by this coordinate Q from the negative charge state. It takes a lot of lattice distortion to get there to the small polaron. So now I have, the hole has a choice to make, so to speak. The hole can be captured by either this shallow state with some capture coefficient CP shallow, or by this deep state with capture coefficient this CP deep. And these two processes have to compete for the same photogenerated hole. Then that means I can have two different PL bands. One from the shallow state where I see there's PL maximum and zero phonon lines are very close to each other. And that creates this UVL band that is very spiky and very, very narrow. That's UVL. Or HEC calculations also predict a very wide PL band from the polaron, where ZPL and PL maximum are separated by large energy because there's large relaxation of the lattice. Again, here you have to move this nitrogen really far away from beryllium to localize this wave function. This UVL is observed in experiment. Where is this? We can understand this by calculating capture coefficients. I have 10 minutes, I think. Is this right? 5? I can't hear you, Walter.
To keep it a little shorter so we have some time for questions.
Okay. All right. So now, two more most important slides. Shockley-Reed hole has a model for PL intensity by recombination. So PL intensity is equal to capture coefficient C times number of available negative acceptors to capture the hole times number of available holes. So for these two states, shallow and deep, I have exactly the same formula for PL intensity from deep state and shallow state. And I have the same number of acceptors and same number of holes. Here I have same number of acceptors, same number of holes. The only thing that's different here is capture coefficients of the holes by these two states. In other words, what's the cross section? What's the likelihood of the hole to be captured? By the way, from this Shockley-Reed hole model, if I find the PL intensity ratio of deep to shallow, it is constant. It's only determined by this ratio of these capture coefficients, which means if yellow or red band, as predicted by theory, and this UVL bands exist together, their intensities must be locked into each other. They have to be the same because these CP coefficients are the parameter of the defect itself. And so, or this particular state, they do not change sample to sample. So in different samples, there could be variations in intensity, but they must be locked into each other. And that's not what happens. In all those three bands that are observed in gallium nitride, as I showed you, the intensities are jumping all over the place by 6 orders of magnitude. So that means that those bands do not come from two different states of the same acceptor. They come from different defects altogether. Okay, now if I calculate this CP and this CP for shallow and deep state, and there is a way to do this by treating, by doing a multiphonon emission calculations. Well, this is, yeah, so this is what I was gonna say. I'm going to skip this. If people want to know how I do these capture coefficients calculations, I can go back to this slide and explain it, how vibrational problem is solved. And the probability is calculated for non-radiative transition from the upper parabola to the lower parabola, depending on the vibrational problem and the electron-phonon coupling. So this I can address if somebody's interested. So we do this for deep state, and for shallow state, there's a different model we have to use because we don't really have a good wave function. It doesn't fit the supercell. But there is a way to calculate capture coefficient by the shallow state and by the deep state and compare it to each other. And if we do, for deep state, I get typical number for typical acceptor in gallium nitride, about 10 to the minus 7 centimeter cube of a second. So it's typical for carbon and magnesium. It's a reasonable number. For shallow state, I get 10 to the minus 6, 10 to the minus 5. So that means shallow state is about 2 orders of magnitude more efficient in capturing the hole. And it means out of 100 available holes, like say 99 go to shallow state, and only 1 goes to the deep state, roughly speaking. And so that means UVL is very bright, and the polaronic band is very dim. It's dark. And in fact, it's probably buried by other bands that created by other defects or the background. And that's the reason why you see this UVL by the shallow defect, but you do not see the band created by the polaronic band. Other bands, we calculated a whole bunch of defects here trying to find them. And we found this red band, which comes from, let me skip forward, which comes from beryllium acceptor vacancy of nitrogen complex. Vacancy of nitrogen is a donor, beryllium acceptor is an acceptor, so they attract each other, form a stable complex, and that creates red photoluminescence. UVL comes from beryllium acceptor, shallow state, and this yellow band on beryllium, it's a headache because the only defect that kind of fits it is this triplet. I'm uncomfortable with that explanation, to be honest with you, because it's a complicated explanation for something that's very common. And that is kind of against Occam's razor, and but that's the one we have so far, and it's the only one we have so far. So that maybe it has to be looked at again. So the conclusion to this is this. Yes, beryllium acceptor does create the shallowest state in gallium nitride at the moment, but it also at the same time creates the deep state, which is actually lower in energy, and therefore under illumination, it's the shallow state that captures the hole, but in the dark, it's the deep state that's going to be the ground state of the acceptor. And so beryllium does not appear to be good for p-type doping still. But what's interesting is that this bistability, these 2 states of acceptor, magnesium does the same thing, zinc does the same thing. These dual things are found in oxides. They seem to be very common. And it seems like, at least in gallium nitride, I haven't looked at it in oxides, but in gallium nitride, this is typical, that the polaronic state is dark and the shallow state is bright, because the shallow big wave function captures the hole much better than a small, very distorted polaronic state. That's what makes it dark. And I think another thing that I want to leave you with is that these hybrid functional calculations allow identification of defects, something that is difficult to do from experiments. So it's a very useful thing to do experiment and theory together. Thank you very much for your attention. I'm sorry I took almost an hour, a little more than 50 minutes, but that's it. I'm done. Thank you very much.
Thank you. Let's see if there are any questions.
Well,
yeah, Kathy.
So just a comment that it seems like this is very hopeful for using beryllium as an acceptor for UV devices.
Okay, so here's the thing. If the beryllium lattice is completely relaxed, then deep state is still the ground state of the hole. So it's not going to create a lot of holes if you dope it with beryllium. At least that's the current thinking. However, there might be a way, and there are some works that people did it for magnesium. There is maybe a way to grow it on some substrate where the gallium nitride is very strained. And the strain can push this polaron to higher energy and making shallow state more stable. And so in that case, there might be hope for making shallow state the ground state of the hole, and then p-type doping might work, but I haven't tried these calculations for strained gallium nitride in case of beryllium. I mean, that could work, but it's a bulk sample. What we think currently is that in the dark, it's going to be high resistivity. It's not going to be p-type because the acceptor level for the polaronic state is 0.6 eV. It's too deep. If you shine the light on it, though, the shallow state captures the pole. Maybe there might be a way to use that.
Okay, thanks.
Yeah, sure.
So can I follow up on that for a moment? So the 0.22 eV for the magnesium, then is that the deep state, or is the polaron state?
It's a great question. So magnesium is not the same as beryllium, and the difference between is the following. So if this is a configuration diagram for beryllium, polaronic state is ground state, and the shallow state is over here. There is kind of energy of 0.4 eV between them. This is beryllium. For magnesium, it looks like this. I have negative charge state, and then this polaron and the shallow state have almost exactly the same energy. So there is so shallow state does not lose competition to polaronic state in case of magnesium, which is why you can dope with magnesium, and that's why magnesium works. Although it's still dual nature acceptor, the deep state also exists, and you also do not see it in experiment. UVL from magnesium you do see in experiment, but not the polaronic state. Exact same situation, by the way. The only difference is energy difference.
Thank you.
Yeah.
So are there other questions? So I had another question, and that is, how do you basically guess how to distort your structure to find the other deep state or the polaronic states?
Yes,
you just try all kind of initial conditions. I understand the concept that there can be, several different local minima, but how do you go about finding them?
Right. So historically, people didn't know about them, and so initially they missed a bunch. But then what they started doing, and that's what I do as well, you start introducing several symmetry breaking distortions. For example, you want to distort beryllium atom, the acceptor himself, either along one of the 4 tetrahedral bonds or along one of the angles between them of this. So you can try some of those symmetry breaking initial points and see which way it rolls. That's how pretty much everybody does this. And ahead of time, there is no way to know. For some of these, by the way, it's interesting. I'm still not sure what's happening. Calcium is right there with beryllium and magnesium. And yet I cannot find shallow state of calcium. It's all localized polaronic states. No matter how I move atoms, no matter how I start, it relaxes into one of the polarons. So, well, the size of the atom is different, so maybe that's the reality. Or maybe I'm just not smart enough to find the right initial condition to find that shallow state of calcium acceptor. So, search for those minima. That's the tricky thing. And the only way I know how to do it is just different symmetric breaking starting points.
Okay. Right. I guess molecular dynamics is still too.
Tried that. Yes, tried that. But the thing is that, yes. You never know if you will jump into that local minimum either. I mean, you have to have enough temperature, and then you have to wait long enough. You don't know how long. It's also, I mean, maybe it's better thing to try MD, and VASP now does this machine learning, molecular dynamics, which can be extremely accurate. So yes, I mean, this is something that I'm trying to, but it's new, so I haven't explored it enough yet. So
okay. Well, if there are no further questions from the audience, or Ozan, you have your hand up, or is that just?
No.
Oh, I just forgot to lower it.
Actually, I can ask one. So I'm a little bit confused.
Okay.
So gallium nitride has 3.5 EV band gap, right? And
yes,
in the beginning of your talk, you mentioned that if there is a deep defect, there can be non-radiative
Yes,
recombination.
that's right.
I'm a little confused that this seems like a large band gap or to allow the recombination. I don't really know about the mechanics of how that works, and it made me a little confused.
Okay, let me explain. So I can go to the picture where I didn't mess it up too much. This one. Well, I messed it up. I'm going to remove this. All right. So yes, band gap of gallium nitride is large, but so what? You just need to emit a whole bunch of phonons to relax non-radiatively, so long as the path for that recombination exists. So if you look at this, so for example, again, if this is my ground state -1, this is my 0 ground state, and now hole has been captured, the system sits in this state. Whether it's radiative or whether it's non-radiative this way depends on the height of this barrier, this potential barrier of intersection of these two adiabatic potentials. If this barrier is low, and for example, there's a bunch of defects that are like this in gallium nitride. Gallium vacancy, for example, is widely believed to be a non-radiative center. There are some others where if you plot these plots, this barrier is really small, like less than 0.1 eV. And so for systems, then it's really easy. And in fact, these transitions are much faster, non-radiative ones, than radiative ones, because all you need to do is just emit a bunch of phonons and roll down to the negative ground state.
I see.
So
Okay.
yes, so it's all how these adiabatic potentials intersect and whether there is a barrier or not. And then there are quantum mechanical ways to actually calculate the rate of this transition for particular defect.
I see. Thanks.
Yeah, sure.
Okay, well, let's thank the speaker again, and
Thank you very much.
I'll stop the recording.